Hello everyone, my name is Pedro Araújo and today we are going to talk about the research called a brief review of all shear correlations for hypersonic flows. This research was developed at the Federal University of Rio Grande do Norte and Aeronautics Institute of Technology, with collaboration of Felipe Maia, Jonathan Araújo, Ramon Carneiro, Ítalo Bezerra, Paulo Toro, Sandy Souza, and Tiago Souza. Okay? Here is present a summary of what will be presented during this presentation, an introduction with the motivation behind this research development, the methodology that was applied, the results, conclusions, acknowledgements, and references. So the main question is, what is the purpose of present research? To understand, we need to know that hypersonic air-breathing propulsion, known as scramjet technology, is one of the most promising alternatives to space access propulsion. Scramjet is an engine that uses geometry to compress the atmospheric air at the compression section by creating a set of oblique shock waves and keep the flow supersonic at the combustion chamber. One of the main aspects of an aerospace vehicle is the aerodynamic drag, a parameter that is essential for predicting flight trajectories. Hence, it was made a review of analytical models available in the literature to estimate wall shear stress and improve the preliminary design of the aerospace vehicle, which operates at hypersonic speeds. And three cases were analyzed considering the supersonic flow over wedge at velocities corresponding to Mach number 3, 7, and 10 at 30 km altitude. The select geometry is a ramp of 500 mm length and an angle of 6.28 degrees, correspond to the first ramp of scramjet geometry as presented in Araújo 2019, Carneiro in 2020, and Bezerra in 2020. Therefore, a brief review of the analytical correlations model used for calculate the friction coefficient for compressible turbulent flows over flat plate will be briefly exposed here. The data obtained by analytical correlations will be compared with CFD data from the numerical approach. The expression to estimate coefficient of friction proposed by White and Christoph uses the CF for incompressible flow, the local Reynolds number, the wall and the adiabatic wall temperature, the recovery factor, and the flow properties at the edge of boundary layer, Mach number and temperature. And Van Driest and Spallanzani use the same transformation function Fc but different correction function to Reynolds number, the Frx. Eckert and Samenchart in the same year, 1955, used the same expression to estimate the coefficient of friction with different constant values of C1, C2, and C3 in the reference temperature calculation. The Meadow and Smart present a different expression to estimate coefficient of friction for compressible flow based on the reference properties density and additive viscosity, which is calculated by reference temperature, almost similar to the Eckert in 1955. Change the value of C2 constant. The computational domain used in the CFD analysis has a 150 mm height and 5 mm entry section upstream of the ramp's leading edge, and the wall was considered isothermal at 300 Kelvin and with non-slip condition. The inlet was set with free stream flow properties obtained from the US standard atmosphere in 1976 for an altitude of 30 km and 5% of turbulent intensity. So, at the outlet, the pressure and temperature were set with 0 Pascal and 300 Kelvin respectively. The domain was discretized using a structured mesh, and the refinement new wall and towards the leading trailing edge were applied. The first layer thickness is 1 micrometer, satisfying the parameter y plus less than 1, which is the required wall conditions in the turbulence model used by the analysis. By the way, the turbulence model was the transition kKl omega. The refinement is also applied towards the leading trailing edge, as mentioned before. Thus, run simulation second ordered upwind scheme and were performed considering a steady state, ideal gas, Sunderland viscosity law, and compressible flow for all cases. The grid convergence index, the GCI method, was applied to check the independence of numerical results with the resolution of the discretized domain. In addition, this study intends to investigate the influence of shock wave thickness in the wall shear stress evaluation. 3 different meshes, one coarse, one medium, and one fine, were used. The refinement ratio adopted between the meshes was approximately 1.5. The GCI method reveals that grid independence of temperature and drag properties are already achieved with the mesh selected. The refined mesh presented a thin shock wave thickness as observed in the Mach number profile at the outlet, and although shock wave thickness is different as we can see in this region, the Mach number downstream shock wave is not affected by mesh resolution. So for all 3 cases, the wall shear stress along the wall ramp is not affected by mesh resolution, keep the same Y plus parameter, which indicates that shock wave thickness does not influence the results related to the viscous effect. The turbulence model used in the analysis was the transition KKL omega, as mentioned before, which considers the transition from laminar to turbulent flow, while the analytical models only consider turbulent flow, and hence the data from CFD analysis will be compared with the analytical models available in the literature after 100 mm in length from the ramp leading edge due to the after 100 mm length we have the turbulent region, and before we have the transition region and laminar region. So relatively to the CFD model, the correlations that predict the similar trend was the correlations derived by sum and short, and followed by correlations obtained by Eckert for supersonic flow Mach number 3, which is the first case, and the correlations of sum and short and Eckert performed better than the oldest models in hypersonic cases, although it underestimates the wall shear. The model proposed by Mead and Smart in 2005 also follows a similar trend of the CFD data. For Mach number 10, the transition occurs at the ramp leading edge, with the turbulent flow almost along the entire ramp length. So, in the conclusions, for supersonic flow with Mach number 3, the best correlations observed were the Eckert in 1955 and Summer Short in 1955, which closely follows the reference data. Okay? For hypersonic flows at Mach number 7 and 10, the 3 correlations that perform better are the correlations derived by Summer Short and Eckert, and the correlations proposed by Mead and Smart in 2005. We have here the case for Mach number 7 and the case for Mach number 10. At Mach number 10, we have the flow is turbulent almost the entire ramp length, while for Mach number 7, we have the transition region and laminar region here. So, Sum and Short and Mead and Smart employ the same equation used by Eckert in 1955, change the parameter to improve the model with the data available. Therefore, one could use CFD simulation to obtain data for different hypersonic cases. Hence, a new CFD-based correlations could be proposed based on the Eckert model. So, this work was financed in part by COPEM and was carried out with the support of Academic Cooperation Program in National Defense. The authors would like to thank the Computational Fluid Dynamics Laboratory at the Federal University of Rio Grande do Norte for infrastructure available, and additionally the authors appreciate the support provided by a group of hypersonic flows. And here's the reference which the work was based on. So that's all, guys. I really appreciate your attention and thank you so much. So see you later.